Good evening and welcome to another BH Futures webinar. Tonight we have an opportunity to explore the reasons behind the durability of ancient building materials and how the Romans were able to build structures that stood the test of time. Our honorable speaker is Mr. Admir Mašić, a professor in the Department of Civil and Environmental Engineering at the Massachusetts Institute of Technology, which all of you are familiar with as MIT. He was born in Bosanski Brod, Bosnia and Herzegovina, and then spent time in Croatia, Italy, and Germany prior to moving to the USA. He went on to study biological materials and chemistry at the University of Turin in Italy. His undergraduate and master's studies were in chemistry, and he earned a PhD in physical chemistry. In 2012, he received the Young Investigator Award from the German Research Foundation, focusing on effects of water on the mechanical properties of collagen-based materials. He aims to develop engineering solutions that will help mitigate the destructive effects of pollution and climate change. To all our viewers, thank you for joining us tonight. Feel free to ask questions in the QA section or the chat, and they will be answered by our speaker either during or after the presentation. Admira, thank you so much for being here.
Thank you, Anna, for this wonderful introduction. And I need to admit, I was very pleased when I received this invitation that allows me somehow to reconnect with the homeland, Domovina. In any case, first of all, I would like to thank Eddie Čustović for the invite and of course all of you to connect from all around the world. I heard you are connecting, and again this is somehow opportunity for us to use digital media to connect, to empower our youth back in Bosnia. This is really the mission of the foundation that Eddie founded, and I think what would be really important to say, and that I recently started this connection with the foundation. I will take part also of this 3 minutes inaugural PhD competition, and I imagine many of you are actually PhD students out there in this webinar, and I really warmly invite you to participate and prepare your elevator pitch. That is really a great way to present your work, but also to showcase your skills. I need to say that most of my positions I went through, and as Anna said, many of those positions were actually facilitated through my participation in the conferences, but also just meetings and connections and networking. So this inaugural 3-minute competition is really something that you should consider in participating, and perhaps even winning some prizes that I heard are not bad at all. Anyway, so today I will touch some of the work that I've been doing now for many years, starting in my second home country, Italy, then third home country, Germany, which I'm citizen of currently, and eventually in the States. And it's about long-lasting ancient materials. But before I start with the ancient materials and how these materials can actually impact our future in terms of design of the sustainable infrastructure, I would like to tell more about my lab and then guide you through building materials of the present and introduce this Antiquity-inspired concept that somehow is getting very interesting, especially when it comes to a sustainable development. And at the end, I will focus on Roman concrete as an example of this design. So this is a Mašić Lab at MIT, and so what we do here is indeed design some really high-performance advanced materials of the present and future, which would include, you see, self-healing cements, damage-tolerant ceramics, or even some high-performance photovoltaic devices. And to do this materials design, we try to learn from two essentially sources. One is nature, and other is indeed ancient world. And you see, especially during my work in Germany, I have been studying biological materials and how these materials actually perform extraordinarily, and how we can extract some of these concepts. So I will introduce you quickly this bio-inspired concept in next slides, and you see this presentation will focus mainly on the left side of this slide. So biological materials, I found them fascinating because nature is able to handle very small building blocks, you know, these nano building blocks. Nano means, you know, 1,000 part of one the micrometer, so it's 10 to the power minus 9, which of the meter, which is really very small unit that then nature manages to organize, and this nature learned through a process called evolution, and we arrived to you know, these high performance biological materials that are somehow optimized for a specific function. And what I have been doing in Germany, and then moved also this work to the States, is finding these materials in nature, and then studying them from a macroscopic through micro scale and down to nanoscale. And eventually, you know, understand these complex structure, function, and chemistry relationships that then allow you to design something that gets close to what nature has been able to make through that process that I mentioned. So you see here are three examples. Bone is you know, self-healing composite made of collagen and mineral apatite, and has a really interesting hierarchical structure that we have been studying and trying to understand, and also processes that occur during the healing, and how these processes might be translated into world of, you know, inorganic world and advanced function materials. Another example here is using actually silicates. This is deep sea sponge that has again a very complex structure that leads to outstanding properties, mechanical properties of a glass. You know, a glass generally breaks, and these sponges show much better performance. And the best example of mechanical performance of an inorganic, you know, mineral aragonite here is nacre. And yeah, recently we just got accepted a paper that describes some micro scale level of microns, these stacks of nacre platelets that play a role in toughening of this outstanding material. I don't know, you're familiar with the mother pearl, I guess, and and this is exactly the same material, you know, nacreous material. So here we are talking about, and this is the new just accepted paper, we're talking about 20 microns scale that actually contributes to the toughening of nacre. So how do we do this? There are many ways to approach this problem, and we in general combine modeling and experiments. My lab is particularly focusing on experimental methods, whereas colleagues are taking care of computational modeling. And our aim in general in this work is really to cover all of these scales through the methods that we use. And when it comes to experimental methods, I'm definitely covering most of these scales through scanning electron microscopy. You will see some results from this electron microscope. Diffraction is of course very important, and key in all this my work specifically is Raman spectroscopy, namely you know, interaction of the material with light that then inform us on the structure that can go down to a molecular scale. So of course, all these you know, spectroscopic and microscopic techniques are correlated then with mechanics, and here, of course, from the macroscopic point of view, we are very much interested in you know, macroscopic behavior, compressive strength, but also we explore other scales through micro or nano indentation and atomic force microscopy. Here is an example of the kind of a big microscope that covers a lot of these functions that I mentioned, that is installed in my lab, and you see this is a advanced Raman microscopy. So you get basically molecular level interactions through Raman imaging, but also it has integrated atomic force microscopy for that mechanics aspects that then you can correlate with Raman. It allows you, for example, to do some irregular surfaces, which are often very important with ancient samples that you don't want to touch or prepare sample before operations. And eventually you like to connect mechanics with all that other signals. So you see very complex characterization platform, but that is the key eventually to you know, move into exploration of complex materials that are biological and ancient materials. So when it comes to biological materials, you see from this slide, I studied a lot of exotic animals that generally were provided by my colleagues around the world, from Santa Barbara to Singapore and so on. We basically were able to identify very interesting and intriguing materials that then led to a lot of technological solutions. Here I show a few examples of those, like this stomatopod is a very beautiful example. Actually, it's very beautifully colored shrimp. It's called mantis shrimp, and interestingly, mantis shrimp is also quite a nasty animal, in the sense that uses these clubs here to break protection shells of the animals around him, and then basically eats them. You know, it uses this this club to break anything. These clubs indeed require a very high performance impact surface, and this indeed impact surface is outstanding that we studied, and the results are reported in these publications here. Another fascinating material is definitely sucker ring material, typical for giant squids. So actually we did go to Baja California to actually catch these big squids, something like 2 meters long squids that have on these tentacles here suckers, and the suckers do have some teeth here. You can maybe see it here. And these teeth are made out of incredible protein that is thermoplastic. And this is quite outstanding because we are not aware of any other thermoplastic protein, and this is the reason why we looked into properties of this protein, publishing series of papers that then led to patents and interesting devices. And the last but not least example here are these threads in the muscles. So these threads, muscles used to attach to any sort of surface. In general, rocks, you know, it's very difficult to detach these muscles from the rock because of the connection that they make through these threads. And the threads are both extensible and hard, two properties that generally is difficult to put together in the same material. This is what actually these muscles managed through a strategy that was published in this paper here quite some time ago. And now I see the dates, and I must say it's already a long time ago, a decade ago. Anyways. So you see, we look into biology as a great source of inspiration, and we are always in search of materials that could inspire our bio-inspired design. But today, actually, I will focus on something different. And I have a question for you. What is the world's primary building material today? Does anyone know? Anyone?
No one responded, but we have a question asking you to clarify something. What do you mean by thermoplastic protein? Can you elaborate a bit?
Yeah, so thermoplastic protein is let me use this quickly. So these are like this suckering teeth, okay? And if you take this material and put it in water and heat to about 60 degrees Celsius, this thing will turn into a gel, okay? And then you can deform it and make, I don't know, some sort of petokraka, okay? And this this thing, upon cooling, will return hard and therefore basically regenerate let's say nanoscale organization that will lead to return of mechanical properties. So it's really as simple as the normal plastic, where you basically melt plastic, change the shape, and cool it down. And that's called thermoplasticity.
And we have an answer from Mr. MD Manjoor Elahi. He said cement.
Correct. Thank you for helping me with with this. So indeed, the world's primary building material is concrete, with its main component cement. And cement production is really constantly increasing, and expected to hit incredible numbers by 2050. These numbers are between 1.3 and 3.4 tons of cement produced per year per capita. Means each of us will account for about 2 tons of cement, because we need that to build our infrastructure, our constructions, or anything where this building material is needed. So, so indeed, that's great. We know how to build with cement and concrete, and we have this reinforcement that compensates for problems of concrete in tension. In compression, concrete is really good, but not as well in tension, and this means that we need to reinforce it using steel in general. So the problem, though, for cement is this number here. It turns out that for each ton we produce of cement, we emit about a ton of CO2 equivalents in the atmosphere, which is really a problem, because it turns out that cement is one of the major contributors to greenhouse gas emissions. We are talking about 8% of total carbon emitted is coming from only from cement, okay? Which is huge, and we don't have quite solutions for that. And you know why it's important to stress the fact that CO2 is a problem. I mean, we are quite familiar with the fact that in past years, indeed, we had increase. I like to show this graph. I don't know if you see here what is plotted, but on the x-axis are years, and here is the concentration of CO2. Okay, and you see these are some of the measurements we know about, and you see it's flat till 1 point. And this is another very difficult question, I must say. I don't know even if I should ask, but if anyone knows what this year here represents, please write it in the chat.
While I give them time to write down the answer, we had one regarding the previous question. Anita asked, wasn't clay before the cement?
Yeah, that's correct. I must say we are talking about numbers here mainly. It's what's primary, not first, okay? So primary in terms of quantity. So that is my answer.
She says,
but
thanks.
we will be talking about ceramics as well. So,
okay, we have an answer from Amina Patak. She says,
yes.
Industrial Revolution, and Anita does as well.
Wonderful, indeed. It's James Watt, invention of steam engine, and that is somehow indeed the start of Industrial Revolution. And we do see this incredible increase, and now exponential path of CO2 that we definitely are struggling to control, and with the solutions and the aspects of our lives that lead to this increase. So, thank you for wonderful answers. I see a very well-prepared crowd. So now, is it really important, this thing? And I mean, we are becoming more and more confident, if not sure, that climate change is real, okay? And projections actually are quite frightening in a sense that we think that between 180 and 320 million of individuals will be affected by 2030. So in 10 years from now, such a huge number of people will be affected, and World Health Organization definitely kind of pinpoint some of the let's say classes of our society that will majorly affected, and we are talking about children are very vulnerable, elderly people, unfortunately, people that live in the countries that are not able to cope with some of these aspects and issues. Outdoor workers definitely are gonna struggle with working outside and needing, being able to resist to heat that is definitely projected to increase. Temperatures are projected to increase anywhere in many parts of the world. Mega cities, small islands could disappear indeed. Coastal, mountainous regions, polar regions, everything is going to be changing in next 10 years. So this is real. This is definitely a problem, and I want to stress that what I said before, 8% of total reasons for these changes comes from cement. So cement production is definitely a challenging place where we can work on reducing CO2 because of these reasons that are showed in this slide. Half basically of the production of this emission of CO2 comes from degradation of the main ingredient necessary to actually make our cement clinker, and this is calcium carbonate. So if you take a calcium carbonate and bake it at about 800 degrees C, you will produce calcium oxide plus CO2, and this CO2 is gas, and this accounts for 50% of CO2. And the other part is definitely burning fuel. So most of the fuels we burn indeed produce CO2 and water, and so that's a problem. The important issue with cement is and clinker production is the temperatures. Is the temperature we need to reach to actually make these reactions to produce clinker, and they arrive to 1450 degrees C. So this temperature actually is incredibly high and requires a lot of fuel. So our aim indeed is to work on that temperatures and reduce them, but making the same materials for the concrete. Good. So let me a little bit tell you about my opinions on how we can work on reducing carbon footprint, of cement. And the one, in my opinion, important solution is really making our constructions in a way so that we use as less as possible of cement and concrete. So use less concrete by design, and of course this has to start from macroscopic to macroscopic projects, and try to really optimize design so that we don't need to pour huge amounts of concrete, but still maintaining, you know, structures in a condition so that they resist and satisfy minimum requirements of performance. Other very interesting perspective is indeed, and you might have heard of 3D printing of concrete, which brings a great, you know, opportunity to place exactly where you want your mortar concrete, and then avoid the parts that perhaps are not load bearing and therefore use less material. That's a really great promise. There are several challenges associated with this technology. It goes from macroscopic, you know, construction side, mixing supply, printing systems. Reinforcement is definitely a problem. It's very difficult to integrate and make rebar using 3D printing technology. And of course, there is a huge effort in making these materials better, especially because we are completely changing the way how we build, and so depositing tiny layers of material lead to many optimization aspects that we need to take into account, and that's more or less what is an important challenge also that we are dealing in our lab. So I mentioned quickly what is actually ordinary Portland cement doing. We need to produce this clinker. So these are like 3 calcium silicate silicates, or halite and belite that are produced at those 1450 degrees C, and then we add a little bit of gypsum and hemihydrate into the mix, and of course we add water, and this is a schematic representation of a complex chemistry that happens during the hydration of cement. You see there is some dissolution, nucleation, growth, and then the final products include mainly calcium silicate hydrate, CSH, that is the backbone of the concrete, cement, and some other components such as calcium hydroxide, portlandite, and ettringite. And so this chemistry here, of course, is very important then to be able to, for example, tune and control 3D printing that I just mentioned. And you see, in my lab, we are getting really close in understanding molecular level transformations of this complex system using some ad hoc setup under the Raman microscope that you have seen in the first slides of this presentation. So second important opportunity that I would like to stress here is extending the life of concrete structures. We do realize that our infrastructure is not great when it comes to durability, and extending a lifetime will mean also less reparation or less reconstruction, demolition, and so on. That eventually will lead to use to less of the production of cement and concrete, and therefore decrease in the global carbon footprint of this material. So that's definitely an interesting concept, and we don't need to go far to find extraordinary, constructions and buildings and infrastructure of the past that actually lived much longer than what is expected life of our structures made out of concrete. And see, this is a Roman aqueduct, but that is about 2,000 years old, where people are still walking. You see here there are people, and it's constantly used as a structure, as a bridge in southern France. But the best example, I think, of this concrete based structure is Pantheon in Rome, which I will spend some time in describing today. So you see, this is entirely concrete, made out of concrete, of course, apart these columns and stuff, but dome and everything is made out of concrete, and it resisted all the environmental challenges till our days. So now, when we think about that, Pantheon, we just are shocked with the evidence that something like that, resisted to degradation, and we do believe that there are some important, features to learn from that specific material, and that brings me into the concept of antiquity-inspired materials design, which is very similar to what I showed for biological materials, but in this case, actually, we have one additional step here. So there is optimization is more or less similar. You have available resources and some civilization that arrived to an ancient technology, but this then technology, was abandoned or left there for, in case of Romans, perhaps 2,000 years. And so it arrived to us in a shape, in the form of ancient remains that guarantee some sort of durability. This time is exactly what we want. It's tested that material that was made 2,000 years ago somehow arrived to us. What didn't arrive was not good in terms of durability, but what did arrive is a great source of inspiration, perhaps, And we have many materials that did arrive to us. Apart Roman concrete, for example, beautiful example is Egyptian blue, which is a material that the Egyptians made to cope with the issue of blue pigment that was quarried, excavated in Afghanistan, and that was the only source in that world, the ancient world, for this blue pigment, and they wanted to use blue, but they couldn't because it was quite expensive, or it would take a lot of time to source it from Afghanistan. What the Egyptians came up with is Egyptian blue. It's indeed a first synthetic pigment, to our knowledge, that shows outstanding properties both in context of durability, but also emits infrared light. That is one of the inspirations, or one of the properties that we look into to optimize, for example, solar cells. Another very durable material, blue pigment, was produced by Mayans, and they used the clay and indigo colorant to create a blue pigment that is resistant to both acids and bases in a boiling condition. So incredibly resilient pigment that is a topic of studies, was and still is a topic of studies in the labs around the world. Last example here is an example of ancient manuscripts. We recently published a paper. Here is the reference. of a very unique technology of making manuscripts that probably allowed this beautiful, especially this temple scroll manuscript to survive 2,000 years, and you can have a look to this paper as well. Today I will focus on the Roman concrete and how the understanding of Roman concrete can inspire, you know, our modern concrete. And of course, we will need to travel across the scales from macro to nano to do so.
We have a question from Leila
Yes.
Hajic. When you mention Afghanistan, do you think of lapis lazuli or?
Yeah, absolutely. Lapis lazuli, correct.
Okay, thank you.
Good. So I don't know, this was supposed to be a video, but you can perhaps check this if you Google or go to YouTube. You will find the history of Romans, and it's you know, picture of time of Hadrian, and you see how extended this empire was at that specific time, and this is definitely an impressive in size and management. And I must say, when it comes to Romans, I'm very much passionate about, because it's somehow wonderful to look how you know, their this history evolved, and how they managed to actually build the outstanding constructions and such a huge empire. So when it comes to ancient Romans, we probably talk about four main achievements when it comes to infrastructure, and we are talking about use of arches and vaults that allowed, you know, to make continuous building, and these shapes that aesthetically would be wonderful, but also in terms of performance, and that was possible also because they invented the concrete. That at that point you were not able to you know, design buildings with some arbitrary shapes simply because you would have blocks, you know, of stones that you need to put together, and an invention of concrete then led to this freedom of designing arbitrary shapes by pouring concrete that would then harden and take solidity. And of course, an important aspect of this you know, Roman Revolution is bringing water to the cities, that then turn the cities into wonderful places to be for, you know, with all the services, but also opportunities to work, but and you know, enjoy living in the city with all the amphitheaters and everything was basically meant to increase the quality of life of all the citizens, and most importantly, indeed, then turn cities into pleasant and hygienic places is bringing the water from the mountains into the city, and through the aqueducts, and that's another very important achievement. The last that I listed here is construction of roads that then allow to communicate and move quickly through such a big empire. Okay, so I mentioned Roman architecture, and you see they used mainly volcanic tuff and travertine stone masonry with the brick-faced concrete, and then put the marble and other stones to decorate as a decoration. But the key, you know, of the backbone is definitely concrete. This is the example of Trajan markets. But here is the example of how they were doing this. It's fascinating indeed to see, because they would you know, make it beautiful from outside, you know, and inside here they would put whatever they found that then would be somehow connected through the mortar that is cement and concrete that I mentioned for so many times now. Good. So opus cementitium is indeed a construction technique that would use a lot of aggregates and binding agent in combination with water to create that solid poured, you know, structure, backbone of all these constructions. I am showing here this print here that comes from a reprint of an important book. It's called the De Architectura. Basically, when you mention Roman technologies, you can't go without mentioning Vitruvius, who wrote this book that describes most of the technologies that were used in that specific time. So he started this book during this peace, Pax Augusta, around you know, the 20 and 30 before Common Era, he is famous for that Vitruvian Man that Leonardo, you know, considered in his notes, and of course 4 elements. I have another quick question. What are the 4 elements of the ancient world? Who knows that? Anyone? Okay, I will let you think about this. And for sure, all 4 elements.
I'm sorry, we have an answer: fire, water, earth, and air.
Correct. And all of these 4 elements are actually part of the Lime cycle that then is a part of the invention also of Roman concrete. So let me say that the architectural and marine Roman concretes are indeed including this lime as a key component, and another essential component that the Romans came up with is volcanic ash. The volcanic ash that then in reaction with lime creates this framework and a self-reinforcing framework that is Roman concrete. You see in this picture here, there are big aggregates, and then there is this mortar here. So that's the Roman concrete on the macro scale. And just to give you details here, when I say mortar, we are talking about fine, very fine aggregates, less than 5 millimeters. And when we talk about concrete, we take also these big aggregates into consideration. This holds for the modern concrete as well. So you see, to reinforce the concept, you need a lime, you need a volcanic reactive component, pozzolana it's called, and water to make our cement that then will go into mortar if we use fine aggregates, or concrete if we use mortar and coarse aggregates. Quick chemistry class here. So when you, I already mentioned this process. When you take the limestone to make the lime, you need to heat it at the temperatures that are bigger than 700 degrees C. I mentioned there like 800, 900 degrees is what we generally use to produce quicklime. And you remember this CO2 that was emitted. And then this quicklime then reacts with water to make slaked lime that emits some heat. And now you see there is a, there is a opportunity to go back to calcium carbonate, back to, you know, limestone-like material by reabsorbing CO2. And this is area lime mortar before Romans. But Romans then put these pozzolans into reaction. And pozzolans would take these, this lime here to another product, not the calcium carbonate that would reabsorb, but calcium aluminum silicate hydrates. And you see, I already mentioned calcium silicate hydrates, CSH, is very similar what we have seen in ordinary Portland cement. So in this slide, you do see the connection between modern and old through these hydrates that are actually the key for the integrity of our concrete structure. So pozzolans, just to give you an idea how they look like, it's a powder. We do use pozzolans as additives to modern concretes, and something else, some other volcanic material that was used by Romans is pumice. And pumice is a volcanic rock that is very light. You see the density, it's a quarter of water, which is really an amazing, very light stone that shows the pozzolanic reactivity. And another material that the Romans did use is indeed a clay product and the ceramics that we call in Italy coccio pesto, and is becoming more and more popular. And Romans would add this material into mortar mixes, and probably they learned this from others because we do find some constructions before Romans, but especially water-related applications of Romans are like pinkish because of the coccio pesto. So this is an example of aqueduct, water-related constructions that we visit every year with my students in Italy, near Rome. So this is the program that I designed at MIT that allows us to go and look into these real old materials, and then we come back to MIT and explore opportunities for us more, Antiquity-inspired design. Good. Returning to concretes, Roman concretes, architectural mortars, and marine mortars. What I didn't mention that's really important, that these blocks, of Roman concrete actually set in water as well. So what is the key ingredient and what is the key reaction is hydration, not anymore CO2 uptake. And this means that these constructions would harden even in the under the surface of the sea, and that's really an important aspect that allowed the Romans to construct harbors and all the infrastructure in the Mediterranean. But in both architecture and marine mortars, they would use the lime and the selection of these volcanic pozzolans that eventually would differ slightly in terms of final products. In the case of architecture mortars, you would have strathlinggite, and in the case of marine mortars, because they are constantly in marine water, some other reactivity would happen, and generally aluminum turbermarite is the material correspondence of cash. So let me give you the recipe for the Pantheon, and indeed they used lime, sand, and pozzolan from Naples, Baia, Scotch pesto, and Pumice, and especially in case of the Pantheon, the top parts of this incredible dome that measures something like 43 meters in diameter, okay, is made, so the top with this oculus here is made out of pumice in general, mixed with pozzolans, because the pumice, we said, it's very light, and because this is a huge concrete structure, allowed these engineers to design something of such a dimension using concrete without collapsing,
We actually have a question related to
Sure.
the stuff on this slide. Leila is asking, what is the value of coco pesto? Does it replace pozzo? Thank you.
Yeah.
Does it replace that other one I can't pronounce?
Yeah, cocho pesto, and yes, the value is fascinating, because turns out that as in a similar way to pozzolans, cocho pesto reacts with lime to produce calcium aluminum silicate hydrates, and that's like artificial pozzolan that you actually could integrate into your mortar and concrete. Let's say, I don't know if this is a good answer for this question. There is a lot of kind of questions around the cocho pesto when it comes to specifically application in the water related infrastructure. Turns out that makes this mortar extremely resilient to water, which we don't know yet what are the reasons. Okay, but we do study this currently in the lab, so I hope we will be publishing something soon. Okay. Good. So this is again a picture from. Oh, sorry. Here we go.
I'm sorry. What is the baking temperature?
For what?
The last thing you mentioned, you talked about.
Oh, cocho pesto is much lower. Like you make it's a typical ceramic, so not more than 500 degrees.
Okay, thank you.
So here we go. Now we are, these questions are definitely connected with this slide here. And the slide is why actually we are so much excited about Roman concrete. And we are excited because we realize that, and I told you already, we have 800 degrees C for calcining lime instead of 1450 degrees C. So we need less fuel, okay, less fuel, lower production energy. We sometimes use recycled ceramic materials to make this. And most importantly, this thing lasts long. And unfortunately for us, and fortunately for my lab, the reasons for this durability is still not clear. And there are many studies, especially done by, but I would like to stress Marie Jackson as a scholar that really brought us a great understanding of what is really happening in Roman concrete. ancient Roman concretes. And from these images, I show it here is just to tell you how complex these materials are because of their chemistry and also organization and distribution in the material at different scales. So these are scanning electron microscopy images. So you see 20 microns. So what are the origins of this extreme long-term durability? And we believe, together with Marie Jackson and other scholars, that there are these fluids of saturated calcium, silicon, aluminum, sodium, potassium that actually crystallize into materials such as trachyndrite in architectural or aluminum tobermorite in marine environments, and constantly reinforce and fill the gaps in this kind of a living organism. And every time that we have degradation, these solutions, these fluids somehow go there and mineralize, crystallize in the pores, which is a good hypothesis. Of course, for us, the key question, and this is specifically to our work, is where the calcium comes from. This is indeed end of my webinar, and what I try to tell you today is that climate change is real. We need to solve somehow issues of CO2 rising. Concrete is an important material that leads to a significant amount of CO2 equivalents that we constantly put into our atmosphere, and working on designing concrete structures and infrastructure using perhaps less material or making it last longer could potentially lead to a significant reduction and therefore more sustainable materials, let's say sustainable future and better material use. So with that, I would conclude. And of course, I need to thank my students, postdocs, colleagues, and collaboration network, instrumentation development guys, and you for your attention. I would also like to leave you with this beautiful quote by Empedocles that says that architects should build as if they were to live 1,000 years and live as if they were to die tomorrow. Thank you.
Thank you so much. So we actually have one more question for the end. What are the current and upcoming topics your group is working on cement-based materials?
Yes, so we are very much interested in durability, as you realized, and we do like the idea of artificial pozzolans. So what we will definitely, and we are, but we will more and more be interested in is how can we create the pozzolanic reaction from scratch, starting from the materials that we can process anywhere in the world, not going to, Rome or Naples and have to, kind of bring those materials in but kind of, be able to design it from scratch and do it anywhere in the world. Other directions are definitely, self-healing of concrete. That's something that is now advanced in the lab, but we are aiming to, design something that once placed in the, once material is placed, it's able to respond to, external stimuli in a way that then by itself heals and eventually brings us into that dimension through inorganic processes more than current solutions for self-healing materials.
And have you explored Roman concrete in sense of heat retention? Is it better or for holding heat?
Yeah.
Okay. Oh, yeah.
I
moderate.
haven't. No, I haven't studied that at all. But I don't think there are significant differences compared to modern. Of course, we need to say always that when we talk about Roman constructions, they are not reinforced with steel, so it would you know, kind of be necessary to take also that into account.
Okay, he says thank you. I think that's all the questions we have at the moment. Wait, let me just check. Yep, that's all. Thank you so much for this presentation. It was incredibly engaging. I especially personally like the part about the limestone, since I really love Egypt documentaries, and I've always like they used it for the pyramids, and like there are usually those like theories which aren't actually scientifically backed. So I really wanted to know the actual chemistry behind it.
Hey, that's an amazing question you just asked, and it's topic that we at one point got interested in, because indeed there are scholars in the world that do push a hypothesis in which pyramids are actually made of artificial stones. The hypothesis that is not such a crazy idea, considering that indeed you could have a small amount of binder for you know, limestone powder. And Davidovitz, this is the person, old professor in France that actually wrote several books around this topic. And also defined an class of materials called geopolymers, which indeed show some sort of polymerization of inorganic silica chains to confer to a material an incredible strength. And that's if you have a little of that and a lot of limestone powder, in theory you can come up with a chemistry that is very similar to the limestones that were used to build pyramids. No one yet managed to entirely prove this right or wrong, but definitely an intriguing theory.
Well, that was really nice to hear the answer to. We actually keep getting questions, so if it's okay with you, we could go through them.
Sure.
Okay.
Yeah, absolutely.
So Leila, again, with a question about baking. Does the baking temperature have something to do with resilience to water? Locally, we can see that temperatures are higher than 500 Celsius. Then what do you use for burning fuel? Does it make a difference?
Oh, I see. So that's a good point. I mean, I would say in general we don't burn. Okay, we just calculate if you have this temperature, what would be equivalent of you know, CO2 required from standard fuels, and you know, you can kind of work around these numbers, and you do an entire, you know, life cycle analysis and the carbon and energy footprint that can be done just by using kind of standard, you know, sheets and a spreadsheet with the numbers. But definitely that's what is attractive for us. So we would love to use to lower all those temperatures and therefore use less fuel. And interestingly, for Romans, these materials also ceramics are generally, because the technology was, I mean, they couldn't even reach the 1450 degrees at that time. So the technology is always associated with what is their, local availability of resources, of wood, for example. I mean, in Egypt, many things are made out of gypsum because they couldn't afford burning trees and making lime, so they were doing things out of stone and gypsum. But what I want to say is, for romance and ceramics, especially Cochopest and romance, turns out that they are baked on lower temperatures, which is even better for us. So if you think about different ceramic things, you would like to go on the lower side, and that definitely will affect its response to lime and water, and therefore resiliency and interaction with these agents. So that's a good lead, definitely, and we are lucky that Romance, didn't have amazing kilns, but something that is just part of ancient technology.
And do your group moving? Does your group move more? And I need to just read the question and figure out what it's saying. I'm sorry.
Sure. More studying cement-based materials.
Yeah, that's the one.
Oh, that one. Yeah. I mean, currently we have one core research on durability of cementitious materials. That's definitely one of the important directions. As I mentioned, we are always excited to look into other materials that do fit with the Antiquity-inspired concept. Perhaps we will start looking into some glasses or glass processing technologies. We are always interested in metallurgy, even though I personally didn't want to go too much into metallurgy, because there is a lot of studies and groups that are looking into ancient steels and stuff. I did go to Japan to see how katanas are made, which is also an outstanding, ancient technology. Then I mean, there are Egyptian technologies and materials are fascinating to me. I do foresee exploring also other things that Egyptians made, and yeah, again, the beauty of the field is that we have a lot of interesting materials, and we are lucky to have also these incredible tools that allow us to look into incredible details from macroscopic to the molecular level, and that's of course footprint of my lab, materials characterization. From the first slide we have seen is the key to work. So if I think about hiring students is always very much around the physical chemistry, and then we apply that knowledge into this specific field.
Thank you so much. We're out of questions. Okay, so
good.
Thank you so much. I personally never had an interest in civil engineering whatsoever. This was really engaging to me. I really paid close attention.
Excellent. I'm glad that you enjoyed, and I hope many others enjoyed as well. And feel free to reach out to me if you have further questions or ideas or anything might interest you about my work here at MIT.
I will definitely encourage all the viewers and the members of the BH Futures Foundation, and I will definitely personally contact you since Egyptology is really a hobby of mine. So I would like to hear this.
Oh, amazing.
This part of things. Well, I guess that's all for tonight. Have a great evening.
Thank you, and you too. Bye-bye.
Bye.